All right, so we've got these vector valued functions, and I mentioned that we'll call that R of t the position vector, because we're going to start in a very similar place to where you started Calc 1, and that is the relationship between position, velocity, and acceleration, because of all the very nice properties that come out of it. So this guy here is our position function, which again, like we said, basically that means that each component is just given as a function, which could be a constant, but doesn't have to be. But they'll all rely on some single variable, in this case, t. So here is our vector valued function, and let me bring that up. That's what this looks like. Let's see, we're doing 0 to 4 pi, so let's match that up. We know that it makes a helix, right? So 0 to 4 pi. It's got a height of just a little bit over 12. It's got a radius of 10. So you don't need that far negative on the z. So let's get some of that off. Okay. So there's our helix, right? This is exactly what we just looked at last time. What we're going to do is kind of look at some of the properties that are pretty cool. Okay. So what I want you to imagine this is the path that a bug is moving, or a particle, and it's going to go move along this helix, right? So we know it has a radius of 10, 2 windings, and it goes up the z-axis. And our position vector is going to be in whatever units our axes are in, feet, inches. It's some linear distance. That's one of those the things about the space curve. It's a linear curve in 3 space. All right, so it's kind of like the edge of the room, not the floor of the room. So it's just one dimension. All right. Now, one of the nice, we'll use feet just because I want to talk about units a little bit, but centimeters, anything would work. So after we talk about position in Calc 1, we talk about instantaneous velocity. Remind me, if we have a position function, how do we find the instantaneous velocity? The derivative, right? So for a vector valued function, all we do is find the derivative of each component. So once again, guys, that's what's cool about the stuff we're doing today. It is really all Calc 1 stuff, just put into a vector and plotted in 3D. So we're going to be doing some derivatives today. So if we had the position function we had before, then our velocity vector would be -10 sine t, -10 cosine t, 1. All right, nothing crazy going on there. That's just taking 3 derivatives. Now, one of the things we want to talk about is the difference between speed and velocity. Velocity is a vector valued quantity, meaning it has direction and magnitude. The magnitude of velocity is speed. Okay. So the magnitude of velocity is speed. So make sure you differentiate between those two. Velocity is a vector valued quantity. Speed is a scalar. It is literally the magnitude of your vector, of your velocity vector. So we can actually calculate the speed of our helix. It's the same magnitude we were using last time. And the velocity vector is going to be tangent to the object's path. So we'll put those on in a second, I think. Let's see. Let's put on our velocity vector. Not that one. All right. So here's our plot. Oh, there we go. And you see that black vector right there? That's our velocity vector. I'm going to take off that blue one just to make sure it's not too confusing. It's the trace vector. It basically goes from the origin to the point, but we don't really need that right now. This is our velocity vector. Notice how it's always tangent to the path of motion. All right. we're going to look at something real cool here. So we've got a velocity vector. We're just going to do this one together. We've got a velocity vector of 10 cosine t, 10 sine t, sorry, negative 10 sine t, 10 cosine t, 1. So if I'm looking at the magnitude of v, it's going to be the square root of negative 10 sine t squared plus 10 cosine t squared plus 1 squared. Okay. Some really cool stuff happens here. So square root of 100 sine squared t plus 100 cosine squared t, and 1 squared is just 1. Perfect. Is everybody seeing the Pythagorean identity in there? Basically, sine squared plus cosine squared is 1. So if we factor out the 100, we'd have 100 times 1. And so this comes out to be square root of 101. And units we're doing is feet per second. Now there's something really cool to notice about this, and I'm gonna point it out in the plot as well. Notice that our magnitude does not depend on t. It could have, depending on what, depending on, this just happened to work out real nice for us. But this does not depend on t, which means that our speed is constant. But our velocity is not. So let's go back to CalcPlot 3D and make sense of this. All right, watch what's happening, and then you'll see it a little better if I look straight down this thing. All right, what do you notice about the length of that velocity vector? It is not changing, right? Which is exactly what it means to have a constant magnitude, or in this case, a constant speed. But what is changing on that vector? Direction. The direction, which is why velocity is not constant, but the speed is. Again, making just that differentiation between the two, right? So, I mean, it's really cool to we can actually see this happening, right? That vector is not changing size. I didn't even put in a space curve for that vector. This is actually pre-built into CalcPlot 3D. So we have a changing velocity. Well, let me see. I might have these not in the order that I thought I did. So let's talk a little bit about direction, and then we'll come back to the changing velocity. All right, nothing new here. We've already talked about, the position vector and the velocity vector. Well, then the direction is basically the unit vector of the velocity. Because what's that doing? That's taking away the magnitude and talking about the direction of that vector that was going around the helix. This is called the unit tangent vector. Let's think about this for just a second. What did we do to find it? Well, we took the derivative. Well, that's how we find the slope of a tangent. And now in this case, because it was vector valued, we turned it into a unit vector, and that's what creates the unit tangent vector. So it's that first derivative of your vector valued function. And then if you normalize it, right, if you divide by the magnitude, it becomes a unit tangent vector. And again, like we talked about before, when you have a unit vector, that preserves direction while getting rid of magnitude, hence the name unit tangent vector or direction. All right. Now, one last thing we got to talk about, and then we are going to do some, okay, maybe a couple less things we're going to talk about. All right, going back to this guy. We said this velocity is changing even though the speed is not. What is the name of the force that changes velocity? Acceleration. How is acceleration related to velocity? It's the derivative. So putting together what's great about this is we're just leveraging what you guys already learned in Calc 1. The acceleration vector is the derivative of the velocity vector, which is the derivative of the position vector. So this is our acceleration vector. Now we can add this to our plot here. And I think it really does a good job of kind of showing how it works. I know you can't see it just yet, but you will. It's that green one. Notice how the velocity vector, or excuse me, the acceleration vector is pointing perpendicular to the velocity vector. Right? And if we look straight down, or as straight down as I can get it, we can see. Now, let's think about why this makes sense in terms of vectors. If the acceleration vector had any piece of a component in the direction of the velocity, then the magnitude of the velocity would be increasing. So it cannot be either in the direction or opposite direction of the velocity, because that would change the speed, right? Think of speeding up or slowing down. So it has to be perfectly perpendicular because we have a constant speed. Because all it's doing is changing the direction. We can see that real clearly on this drawing. See how it points towards the center at all times as we go around our helix? Because all it's doing is changing the direction. So a lot of cool properties. And again, it comes from stuff that you guys have already done. It's just now we're looking at it as a vector valued function. Oh, lost my dots on the dot product, unfortunately. But, you know, these are just a couple properties for doing the dot product of vector. You would dot u dot v, if you're doing the derivative, of the dot product. I mean, you can always do the dot product and then take the derivative too. So this is just a couple properties for the dot and the cross product. I don't want you to worry about those too much. Those aren't going to come up, but I want to go on. Just last thing we're going to talk about antiderivatives of vector value functions. Well, hey, we just saw taking derivatives of vector value functions. We can go the other direction too. For instance, if we have a velocity vector and we want to recover the position vector, we would do the antiderivative. So you're just doing the antiderivative of each component. Now, if we do not have an initial condition, we do have to still observe the plus c because we have a general antiderivative, but you can just put a plus c with a hat on it, and that's representing a constant vector at the end. Or you can put a c on each component, that'd be fine too. Just use, if you do a c for each component, make sure it's like C1, C2, or C3, or A, B, C, because they can all be different values. And last thing is we can have definite intervals of vector valued functions. That would be if we're trying to get some kind of net change in the vector value function, distance traveled, or depending on what what we're taking the integral of. All those properties that you learned in Calc 1 still hold. And so you would just do 3 definite intervals. So like I said, we're going to get to do some calculus today, but as of right now, it's just going to be the same calculus you did in Calc 1. We're just doing it on vector valued functions.